Hello. Today we are going to talk about Stokes formula as well as we are going to get an expression for terminal speed. We are having a solid sphere which has got radius r and liquid in a container, a column. The density of the solid sphere is rho, and density of the liquid which is filled in the column is sigma. And when we drop that solid sphere inside this liquid column, this sphere will get into the liquid and it will travel through the liquid and the speed increases. And at the same time, the viscous force or drag force also increases. The viscous force, which opposes the motion of the solid object, increases when the speed of the object increases. And Stokes got the relation between this viscous force and the speed, and he put it in this way, and this is actually called Stokes formula. Here it tells that the viscous force increases when the speed also increases, where r is a radius of the sphere, that whatever the object we are going to drop, and neta is a coefficient of viscosity of the medium. So it depends on what liquid we are going to take inside the column. If it is water some value, if it is honey one value, if it is mercury one value, it depends on what fluid we are going to take. Now what happens is this solid object will move through the liquid and the speed increases, but after certain distance the speed will not increase anyway, or the speed of the object will remain constant. That speed we call it as terminal speed. Let me tell you why it happens. Now we have got to know that when speed increases, viscous force, the drag force which opposes the motion, also increases. So now let me find what are the forces acting on this solid sphere. You have got a gravitational force which is nothing but m into g, that is mass of the object. You have got a buoyancy force which is actually upward thrust, I call it as Fp, as well as I got a drag force, or we call it as viscous force, Fv. Now we have got these three forces acting. Initially the weight is actually greater than some of these forces. These two forces are in this opposite direction compared to the weight. Since weight is greater than some of this buoyancy force and viscous force, there is acceleration, net acceleration along the downward direction. That's why this ball moves with a greater and greater speed. And we have got to know that when speed increases, the viscous force also increases. This is actually called Vfv, viscous force. It happens that after attaining certain distance, the weight and some of this balanced, Fp plus Fp. Now initially weight is more, and as it goes inside the fluid, speed increases. At the same time the viscous drag force also increases, so that the weight and some of these balance each other. And when the total forces acting on the object is zero at certain distance, I can tell that acceleration is actually zero. It means that there is no change in speed, or speed or velocity remains constant. That speed we call it as the terminal speed. So the terminal speed is a speed attained by the solid object inside the fluid medium when the total force acting on the object is equal to zero, or the acceleration becomes zero. Now we are going to take this expression as a expression for viscous force, and we are going to find out what is this expression for the terminal speed. Now this is actually weight of the solid sphere, which is actually m into g, where m is a mass of the solid sphere. This is actually for the sphere, which is equal to this condition I'm going to take, and I'm going to find out what is a terminal speed Vt. This is actually a viscous force, actually that is 6 pi neta rv, where v is a terminal speed. It attains certain speed, we call it as terminal speed, plus this buoyancy force is nothing but weight of fluid displaced by solid object. According to Academy's principle, whatever the weight displaced by the object, that is actually called as buoyancy force. So how much is that? It is actually weight of the fluid, which is nothing but mass of the liquid or fluid, into gravitational acceleration. So I'll write it is m into g, where m is the mass of the fluid. Now mass I'm going to write in terms of density. Density is equal to mass by volume. So mass is equal to density into volume. Mass is equal to density into mass of the sphere. Volume is 4 by 3 pi r cube, where r is the radius of the small sphere. So this is actually rho 4 by 3 pi r cube is equal to 6 pi neta r Vt plus, this is actually mass of the fluid displaced by the solid object, which is nothing but a density of the fluid, which is sigma, into the volume. So volume of the fluid displaced by the object is nothing but volume of the object itself. So that is a 4 by 3 pi r cube. It's nice to cancel pi all over, and you're left with let me just take outside 4 by 3 r cube, and this is sigma minus rho is equal to 6 pi cancel neta r Vt. So one r also I lose, so I want to get an expression for terminal speed Vt, which is equal to this is 2 by 9 neta r square, and you've got g. I missed g here. I missed g here, g, and here also g. I missed g. Sorry for that. So this actually g and also g, and you got rho minus sigma. So this is an expression for the terminal speed gained by this object after attaining certain distance. It means that terminal speed directly proportional to r square, and terminal speed is inversely proportional to neta, and terminal speed is directly proportional to rho minus sigma. So if you have greater volume, or I mean if you have got a bigger drop, it has got more terminal speed because it is directly proportional to square of the radius. If the fluid has got more viscous coefficient of viscosity, that means the viscous force is more, then you've got less terminal velocity. If the density difference is more, then you got more terminal speed. So that's all for today. Thank you for watching this.